I can't remember. 8.4. We're in 8.4. So this is section 8.4. We're kind of jumping in here. Okay. Everybody tell me what they think probability means. Yes, Jonathan.
It's the chance of something happening.
Yes.
The amount of time.
The chance of something happening. Okay? That's kind of like, okay, what kind of chance? Okay? So, what is an event? What's the probability of you going to Mars?
0.
0. Okay. Why did you guys say 0?
Because I don't want to go to space. It's like 0.0000000.
Okay. For all likely purposes,
Okay.
it's 0 because probably you being selected to go to Mars at this point when we haven't even sent anyone to Mars is probably impossible. So
The probability of it being probably.
So 0% probability is something that's really impossible, okay? The possibility that you're gonna grow a third arm is 0% because it just doesn't grow, okay? You're not gonna grow a third arm, okay?
You have the technology to make that happen
I-
if you were really willing.
Right now, you will not naturally grow a third arm. Okay, let's stop the different scenarios, okay? What is the probability that you will go to bed tonight?
At a time or like?
No, what's the probability you will go to bed tonight? I didn't say you're gonna sleep. 1,000,000%. What does 1,000,000% mean?
I'm going to bed because I'm already tired.
0.2.
Okay, you guys are not being serious, so I'm gonna stop the questions, because if you can't answer seriously, it just makes it kind of chaotic.
100%.
Okay, 100%. So the probability of something guaranteed to happen is 100%, okay? I know some of you are being funny by saying I'm not gonna go to bed. I bet most of you go to bed at some point. I didn't even say you had to go to sleep. I just said, don't argue with me, please. Okay, this is not an argument.
The probability should be 100.
Okay. Most people at night go to bed. There are very few of you, I would say probably none of you, that don't go to bed at night and sleep, because you would be absolutely tired if you never went to bed. Okay, you would not be functioning right now if you didn't go to bed. So there is 100%, it's guaranteed to happen, okay? So probabilities go from 0% to 100%, okay? What kinds of numbers are those? If I were to talk about 0% to 100%, what numbers are they? What is 0%? Yes.
It's a range between two numbers.
It's a range between two numbers. How do I write 0% as a decimal?
0 repeating.
It's just 0, isn't it? 0.0?
Repeating.
Does it matter if I repeat it?
That's the full thing.
Okay. How do I write 100% as a decimal?
100%. 1.
It's 1. It's 1 because remember, percent really means divide by 100. So if I have 100 divided by 100, because this is per means divide. And cent means 100, that's the, just the Latin century is 100 years. The number of cents in a dollar is 100. The prefix cent means 100. So per cent is per, which means divided by 100. So 100% is 100 divided by 100, which is 1. So percents are always between 0 and 1, or probabilities are always between 0 and 1. Okay? You can't have a bigger probability. You can't have 200% of some chance of something happening. Okay? It just doesn't work. You have a probability you can never have above a 1. Okay? It's just not ever going to work. Okay? So that means there's all kinds of fractions in between here that probabilities could be. Okay? All sorts of fractions. Those are the exact probabilities. A fraction is an exact. And a decimal, like 0.25, 0.5, and this one is going to be something different. Let me see. 19 is 0.47368421, and it keeps going. Okay. We don't usually know that number. These are approximations. Now these are actually exact if they stop, but if they don't stop, they are approximations. So a lot of times we can write probability as percents, we can write them as fractions, and we can write them as decimals. The most accurate is as a fraction. Okay? So that's the most accurate way. The exact way is as a fraction. Percents are still rounded depending on what you're making it. Decimals are still rounded depending on what you're making it. Okay? So we're going to look at how do I define probability? What is the definition of probability? How do I determine the probability of something? Does everybody have this down? I want to.
No.
Okay, so when we define probability, when we're talking about the chance of something happening, how we find out what's called the theoretical probability. Okay, this is theoretical. We'll talk about a different kind in a minute, but theoretically, is defined as the total ways of getting whatever you're finding probability out of what's the number of the specific event. Let's give an example because that sounds kind of funny, okay? Sounds kind of funny. So if I have a dice, okay? It's a dice, sorry, I have to get one. Okay, everybody know what a dice looks like?
No.
How many numbers does it have on it? It has 6. So if I roll a dice, how many numbers or how many different ways could I get an answer? There's 6 total ways because you have the probability of all 6 numbers. If I say I want to roll a 1, how many 1s are on this die? 1. So this would be 1 out of 6, theoretically. So that means if I were to roll the dice, every 6th time, I should get 1. That's in theory, because that's not going to happen. Because when you do the experiments, it doesn't always work exactly like in theory. You're going to do some practice tomorrow, rolling specific events. And you're going to see that if you do it enough, it will come close to the theory. Okay? So let's say I roll, my event is I roll an even number. Now I know what the probability of that is on a die. Okay? Yes. It's 3 out of 6, which reduces down to a fraction of 1/2, which somebody said 50%, which I will take that because 1/2 does stop. And so it's a 50% chance. But this is how we usually leave it most often, is as a decimal. Because if you take 1 and divide it by 6, you do not get, so like 1 divided by 6, you get this. This is 0.166 repeating. Okay? That number never ends. It continues to go. So the exact answer is 1/6 instead of this. Okay? But I could say it's about 16.7% of the time. Because 0.166 changed into a percent. We're just doing the opposite. We're going to multiply by 100 to get that percent. So those are the ways, theoretical probability. Okay. So if I were to choose, if I had all the letters in the alphabet, and they were those magnetic letters that you can stick on the refrigerator, and I had all of them in a box, and I just randomly put my hand in, what's the probability that I will get a vowel? So first of all, let's see, how many, let's look at we're looking at for letters in alphabet, and we want the probability of getting a vowel. Okay. So how many different letters are there to start out with? 26. Okay. There are 26. How many vowels are there, Jonathan?
5.
There are 5. I heard you say that over there. Okay. So my probability is 5 out of 26 that I will get a vowel just by randomly grabbing in there and pulling one out. Okay. So that's how we define probability. It's how many chances you are of getting one out of how many different ways you could have gotten, how many different choices there were. So this is really the number of choices, and this is the number of choices of what you're talking about, vowels. Okay. This does not reduce into any simpler fraction. If you wanted to do percentage-wise, that is also going to be a rounded number. So if I did this as a percent, you would do 5 divided by 26, which is this decimal, 0.1923. That's rounded. Okay. To make it into a percent, I multiply by 100, so I get 19.23%. Notice, this is the most accurate. It's the most exact form. Fractions are always more exact than decimals or percentages because we are rounding. Okay. So these are all the same numbers. Those are all equal numbers. These are just approximated. Okay, very close, but they're approximated. Okay. I didn't spell alphabet right. It's normal. Alphabet. Okay. So that's just finding out a simple probability. When we start combining activities, let's say I roll 2 dice. Okay. We have to talk about what an independent event is. Independent events. Okay. So if you have more than one event, so if there's more than one event, example, I'm going to roll a die and then I'm going to throw a coin. Okay, I'm doing 2 separate things, correct? Okay. Does rolling a die impact throwing the coin? Are they independent of each other or does one depend? So if I roll a 6 over here, I'm determined I will throw a head over here. I will get a head because I rolled a 6. Is that true? No, they're not dependent on each other. They're independent. So independent basically means one does not affect the other. Okay, so I'm going to give you some out of the book. I'm going to ask you if you think these are independent or dependent. Okay. Okay. Is this independent or dependent? It rains on Monday and it rains on the next day. Is that independent or dependent? Are those 2 things dependent on one another or are they independent of each other? They're independent. You have a different chance of rain each day. Okay. Now, sometimes we have systems that rain come through, so that's not as clear cut
Right.
as I would say. Okay. So, Jayla's volleyball team wins and her brother's basketball team wins.
No.
Are those 2 events independent of each other or not?
No.
They're not independent of one another? So, if
yes, they are
Jayla's
independent.
volleyball team loses, does that mean that her brother's basketball team's gonna lose?
No.
So they're independent, right? Because they don't affect each other, okay? So, let's see. Ouch. If I roll a die and I get a 2, and then I pick up the die and roll again, and I get a 4, are those things independent of one another or are they dependent?
They're independent.
They're independent, that's correct. Because it's 2 different rolls, so one roll does not affect the other. Okay, let's show you a dependent one. If I pick out of the alphabet an A, out of the alphabet I pick the A. Next, I go into that same alphabet that I had, that I picked the A out of, and I pick a Z. Are those dependent or independent?
Independent.
They're what?
Independent.
Why do you say that?
Because they're different letters.
They are different letters, but does anything change?
Yes. You're not
Yes.
gonna pick the A again.
You can't pick the A again. You don't have that choice anymore. Okay? So they're dependent because you have less. Okay, guys, let's pay attention and stop breaking back and forth, okay? Okay, so let's think of it this way. if I had 10 cents in dimes in my pocket, if I pick one penny out, did I say in dimes?
Yeah.
10 cents in pennies in my pocket, okay? If I pick one penny out and then pick another penny out, are those independent of each other?
Dependent.
They're dependent because I've already taken one out. So now the probability of choosing another one is dependent because we have less to pick from. Okay? So that's the idea of independent versus dependent. Okay? When they're independent, then you can take the probability of the first event and you multiply it by the probability of the second event, and that gives me the probability of the combined event. So let's think about this, okay? So let's ask ourselves, what is the probability that I'm going to roll no, I'm not going to do that one. I'm going to roll a 5 or 6 on a die, and I'm going to, these are the two events, and following that, I'm going to throw or flip a coin and get heads. Okay, so there's my two events. Let's figure out the probability of each. Okay. What's the probability that I will either get 5 or 6 when I roll a die? What's the probability of that?
2 out of 6.
2 out of 6, because there's 2 possibilities out of 6. So the probability here is 2/6. Or I could reduce it to 1/3. So that's the probability of that event. What is the probability when I flip a coin I will get heads?
100%.
Or 1/2 as a fraction. We want to do these as fractions because we want to keep them in exact form. So you want to do them as fractions if you can. Okay. So the probability of these events combined is you take the probability of the first event and you multiply it by the probability of the second event. So it's 1/3 times 1/2. So the probability of this occurring, that you get a 5 or 6 and a heads, is actually 1/6, because I multiply those together. So the probability of both of those things occurring when I do those is 1/6 of a chance, which is, if I put it in the calculator, is 16.7% rounded. Okay, that's what the percent is, it's rounded. Okay, so that's what we're looking at there. Okay. When you come back, we are going to we're going to do some theoretical probabilities of different things. Then tomorrow, when you come to class, you will be doing those experimentally. So I'll kind of explain that. So we're going to write down our theoretical, then you're going to do them experimentally and see what happens. And then when you come back on next Tuesday, we'll talk about those differences. Okay? Okay, so go ahead and take a break right now.
Oh.
10 minutes, always 10 minutes.
My brain is fried. Why? I bought a whole bunch of big pocket
That's a tiny one. This is the brother in question. This is a very bad picture. This is a very bad picture of him because I did it simply because he hates pictures. Oh. Yeah. Why is he like? He's 26.
Hey,
Your dad's uncle?
Yeah.
Let's go walk around.
Oh my gosh, I went up to this beautiful man.
Hayden, you help me. I'm gonna grab one.
One. Okay.
I have to look at my key. Where's my key?
Rise.
Can you guys show me how it works? You have to get more.
Marshall, you're gonna be getting a big prize for tonight, man. For what you did.
Go made it for me, Dad.
Thank you.
It's a mess.
Welcome.
That's so long. I know.
And keep practicing, okay? Practice at home.
This
Okay,
beautiful man added freckles.
Lillian.
Yes. I get the pink one? Yay!
Wait, what
This is the best pack of candy.
what's the gift card
Oh,
for?
Huh?
What's the gift card for?
I don't know, what do you want it for?
Dust.
Okay.
no. You should get Amazon one. No.
That's what it's for.
Oh, that's a crusty little bottle.
I was looking at one of these packs and the wrapper was off. So I didn't buy that pack, but the wrapper was off one of them.
That one was definitely on the back. It is a butt chin. Have you never seen a picture of
I
you?
have, but
They
those
always have butt chins.
no, they have like a straight line for a chin. It's like a literal straight line. Your ruler cannot make a straight line. Have ever seen a picture?
No.
Oh, it's Get some note cards and practice those multiplication cards at night, Peyton. Right? The more you practice with that, the better you will go on that. I'm being honest. Because the more you practice that and get it down, the better you will do it now.
This shit has to be any sweet here.
Is that for tomorrow?
We're getting it ready. We're gonna figure out some theoretical things.
Oh, I see what you're saying. So that'll be for tomorrow on the right, but then the part on the left will be for today.
Yeah. Get these two.
Are you gonna lose them?
Yeah, they will.
Fast foods that
Okay, so this really makes me touch animal memory, so they don't want
Jonathan. Jonathan, come here.
Oh,
Wait,
I think I got one.
Miss Miller?
Am I the one that got the exact same?
No, Ezekiel was one. Or maybe you were.
I think I got last.
Ezekiel got the exact same.
Oh,
Oh, I did?
You went down by 2.
Wait, I feel like it's less. I feel like
I
I
got
less.
61 and 61.
Was 16?
Mhm.
I thought it was
Yeah, I
less.
keep track.
I thought I got less.
Could I choose just like a blue one of these?
If you can find one. She just filled it in. Nice try.
If you had one more second on the clock.
So multiple linear regression is a thing, right?
Yes.
Where you have more than one independent variable. Yeah, that's what I
No.
was thinking.
More than one independent, more than one dependent.
Oh, it's more than one dependent. Oh,
I mean, you can do a lot of different things.
so when do you have
depending on
different independent variables?
different
Or
independent?
do you ever?
You can have different independent
More inputs,
variables.
right?
Yes,
Multiple
more
inputs into
inputs,
an
yes, and it
equation.
comes out, yeah.
Right, yeah,
So
yeah.
then you do, it's a lot harder. So your linear equation has many more.
It'd be like a polynomial,
It's not really a polynomial. What it is
okay?
it actually becomes a linear equation with many variables.
Yes, it would be systems of equations, yeah, or
It's
not.
not even that, it's just gonna be.
X, Y, Z.
Yeah. So you
okay.
have multiple,
Yeah, yeah,
so the more factors you put in, the harder it is to correct. So you you have to, that's a harder thing to find out, so you have to plot different points.
And you would still do
ones
like a
to-
line of best fit that you
Yes.
try to create or
Yes.
somehow, okay, alright.
And that takes some that is really different.
That's what they would do in high level math for a lot of things, right?
Yes, you do a lot of, then you do a lot of matrices and stuff to do that.
I went and I got a bunch of kernels for corn, like from a popcorn thing. I had about 5 bags of popcorn. And I spilled it. We all walked to the forest and I could give them back, but I dumped them in. And we all kind of we're just sitting there looking at the stars like this. And they're just like sounds like gunshots. And the fire starts exploding. Kind of make it so scary, so funny. It's like shooting everywhere. It's just opening.
What, you crashed the car?
I think it was because it was feeling it. He was probably peeking glances at us.
No, is there a reason you gave me traction?
Ezekiel, would you put your name on it, please?
My brother.
I usually know for sure.
I need to get new laces for these. They're like
Branson.
braces. I already have braces.
Come
Sorry.
on up here. Branson,
I already have
Branson, come on up.
Oh.
Wait, can I put it?
What?
Yeah.
New braces? I don't have any. Yeah, right. I would have put
What?
Wait, which shirt is that? Which one are you? I should
No, because you're the same. Gotta go up.
What's your, so you know like one of the news bikes is Florida, MX5, that's the one I'm gonna get. This is 6.
Okay.
Have braces in that.
Get ready to sit back down, please. Get out a piece of plain paper. This is a worksheet you will finish tomorrow. This is some problems you will finish tomorrow. So you need a clean sheet of paper.
I said, that's what I said, I said there's multiple independent variables.
I said you can do that. But to get the actual fit, you notice there's a million different fits there. Okay, to get the one that goes with that, then you have to put those all together. And that's higher level math. Okay,
I want your grandpa. What? Not that way. I want your grandpa as my grandpa. How about that? What? You guys can be friends. I don't have a grandpa. Well, I mean, I don't remember him that much. It's kind of sad
mean, they only died like a year ago, but.
Did you guys like the option?
Huh?
Did you guys like the
No, that's the other side. Okay.
Okay. What I want you to do, so it looks kind of like this, I would like theoretical to be a little bit smaller. So you're making a column on your paper that says theoretical. It needs to be a little bit smaller. Then you make one that says experimental. It's gonna hopefully a little larger on your paper. And I wrote 30 trials, yes and no. I will explain all this right now. I just want you to title it like that. Okay. So what we're going to do is we are going to calculate the theoretical value of doing some things with cards and dice. Okay? And so we're going to figure out theoretically how many times should you get this. And then you're going to see if when you do the experiment tomorrow, you say, yes, I got that, or no, I didn't get that, and you're looking for the probability based on the experiment. Okay. Now, in statistics and math, we sometimes have to rely on the experimental to give us the probability of something happening. You will notice to get experimental, you have to do it many, 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 many times. So, to do experimental, you have to do it many, many, many times. And sometimes that's how we figure out what the probability of events are, is by doing experiments. It's not because we can do it by theory, because we don't know the number of occurrences that or number of times it will occur in the total possible ways that it can occur. Okay, so it makes a difference. So I want to show you some things here. So our first event that we are going to do is rolling a die, or rolling a 4 on a die and choosing a red card from a deck. Okay, so our two events are rolling the 4 on the die and choosing a red card in a deck. Okay, so theoretically we can figure this out because we know what the events are here. Okay, what is my probability of rolling a 4 on a die?
1/6.
1/6. Okay, so this is the probability for that. What is the probability of choosing a red card in a deck of cards? So basically what I'm looking at is right here, without the jokers in there. What's my probability of choosing a red card? How many of you guys have worked with cards, played cards? Okay. What's our probability of choosing a red card out of this?
1/2.
1/2, because there are same amount of red cards as there are black cards, if your deck is full, okay? So it's 1/2. So our probability of these two things happening is 1/6 times 1/2, which equals 1/12. So that says about every 12 times you do this, you will get a 4 and a red card. So tomorrow when you come in, you will be given a die. You will work with a partner. Okay? You will roll the die. If you don't get a 4, you don't even have to draw the card because right away you didn't get it. So you would put it in that no column, okay? But you can do it at the same time. So one person is rolling the die, one person is picking the card. When you're picking the card, each time you will put the card back in, but shuffle the cards so you know they're mixed up, okay? So you pick a card, I'll roll a die, okay? You pick the card, I'll roll the die. Let's do it at the same time. Okay, go. Okay, I got a 5 and you got a black card. We didn't get it. So we would mark tomorrow, no. You're gonna do this 30 times. You're gonna do it 30 times, and you're gonna look to how many yeses you got compared to how many times you did it. So it's out of 30. When you do it tomorrow, it will be out of 30 because you get how many yeses, but this helps you keep track of how many numbers you've done. Yes,
What's the rest of the space you need for?
because I haven't given you the other theoretical ones. You're gonna do other experiments. Okay, so we're gonna do other experiments. Okay, yeah, so this is one event. This is event 1. What you're doing is rolling a 4 and choosing a red card. We're gonna make it more difficult, okay? So now, our next one is rolling an even number and choosing a heart from the cards. Okay, so theoretically, Jonathan, what is the theoretical probability that I will get an even number when I roll a die? 1/2. Okay. Marcy, this is a little harder. Okay. We're going to see if you know, but if you don't, we'll help you figure it out. Okay. Do you know what the probability of drawing a heart is? Do you know how many hearts are in a deck? Just a minute. In a deck of cards.
1/4.
Okay, it is 1/4 because there are 4 different suits, correct? Okay, so there's 4 different suits, so it's 1/4. Okay, so my probability is 1/2 times 1/4. Well, that's a little bit better probability of getting this because it's 1/8. Okay, so you're gonna then do your yes and no's. Again, you're gonna do that experiment and see what you come up. So we've got the theoretical, then you're gonna do the experiment with yes and no's. And each time your answer will be out of 30. Okay, because it's how many yeses you got out of 30 rolls. The reason you're keeping track here is in case you lose count of how many times you've done it, you've got it right here. Okay. So the next one is going to be the event 2 or 3, sorry. 3 is going, and I'm just going to give you the events now, and you're going to work on trying to find their theoretical probability. Okay. So event 3, this is going to be your assignment now. I'm going to give you these events. Okay, you go on the back, that's fine.
Oh, wow.
They might be doing their experiments for a while.
Oh, yeah, but 30 trials goes pretty fast. Oh, 8, 10. If one person's doing one thing and one's doing another,
Right,
they can do
okay.
it pretty fast. Okay, there's my things. Now, I'm gonna give you, so if you need to count up theoretical probabilities on stuff, I'm gonna give you a deck of cards right now so that you can see where they are. Thank you.
Are we doing this at all at home?
No, right now you're gonna do this. You're gonna figure out the theoretical probability. So I'm gonna give each pair a deck of cards. I think you know the probabilities theoretically for the flipping a coin or for the rolling a die. But if, I'm gonna come around and double check your work. So will Mr. Miller, he will be coming around and checking your work. But some of you may not know in the deck how many queens there are or how many cards there are altogether and stuff like that, okay? Yeah, I want you guys to figure it out, so I'm gonna give you a deck of cards that you can use. We are not using jokers in the deck of cards, so if there's a joker in yours, please take it out if I gave you one. That's a joker. I think the jokers are gone from here. Okay, so there's the total deck, so you guys can use it together. Okay. It's one joker. Marked cards, I tell you, marked cards. I don't find another joker. There may be another joker in here. Okay. But this is to count to see how many there are of certain things. I have to figure out how to get this off. Look at these. So, by the end of class, you should have all the theoretical probabilities calculated. By the end of class, you should have all the theoretical probabilities calculated.
Alright, let's do this. 4, 5 over 6.
And then I will have some problems from the book also to finish, but those don't have to be done in class. Yeah.
Are we gonna turn in this assignment?
Yes. Yes.
Wait, are those 3 fractions? Number of
Yeah, that's 3 different things, so it's 3 fractions, you multiply them all together. There's 3 different events, you still multiply all 3 probabilities together.
Wait, this is due tomorrow Wednesday or next Wednesday?
Okay. So tomorrow you're going to do the experimental probability. Today you're doing the actual theoretical probability. So you are finding the theoretical probability of each of these events. Tomorrow, you're gonna come in and do experimental probability where you actually draw cards, roll dice, flip the coin. See if you get those three things all together and how many times, so you see the experimental probability. Okay, so here's another set of cards.
I'm not.
Work it out.
I'm not.
Did I drop one? Why is
I
that?
don't
So that's, no, an ace is
Oh,
okay, an ace is in the card deck.
Yeah, but then you can make it into one third, so you don't reduce it.
Yes, you can. You can reduce it. If it reduces,
Doesn't that make the probability different?
no. Isn't 1/3 the same as 2/6? Should be the same.
Yes, we do. There's 4 queens in
Okay, right now we should be figuring out these probabilities. We shouldn't be playing with the cards. We should be using them to figure out the probabilities.
See how many cards are on it.